Hello, welcome back to my channel, and in this video we are going to solve this JEE Advanced Physics. Let's read the problem and see what do we need to do. So you have an infinitely long wire located on the Z axis carrying a current in the positive Z direction which produces a magnetic field, and you need to calculate the magnitude of a line integral where you have this dot product of BL and you're given a path along a straight line from going from this point to this point in 3D, and you need to calculate that. You already know the magnetic field because of a long infinite state wire that you should remember. So what this exactly is asking is how much this magnetic field is aligned with this path. That is what you want to calculate. So this should remind you of Ampere's law, okay? But there is a caveat in the Ampere's law. So the first thing you want to notice what is this? This is the line integral, which will tell you how much the magnetic field aligned with your path, and you need to calculate the magnitude of that. And they given you a path which you can see it's only changing in x direction. Y is constant and z is 0, which means it's happening in xy plane because z is 0, so it kind of become easier. So there are kind of couple of ways to solve this problem depending if you have learned how to solve line integral and you know how to write thing in polar coordinates and all those things. So let's do it both ways. One is a longer way and then the other one would be a easier way. So first let's go through kind of a longer way and see how do we can solve this problem. Okay, so let's first just make a diagram, see what we're dealing with. So this is my x. Okay, so now you have made a graph of what this picture look like. So if you are looking at the magnetic field because of this current carrying wire, you will see the magnetic field would be around like this. Using your right hand rule, you can see magnetic field will go around like this and this. So you want to see how much the magnetic field is aligned with this path. That is physically what you're calculating. Okay, so first thing, if I don't think about Ampere law, I just think about a mathematical question. Let's do that way, and then we will think more physically and how can we get the answer. But when I'm thinking about this as a mathematical, I'm assuming you know how to calculate line integral, which I'm not sure if you guys have those in your mathematical course or even in physics course. So, but we will go through it anyway. It's not very hard, even if you haven't done it. So let's go. We know the magnetic field is goes by this of due to straight long wire is going around this azimuthal angle. It's going around the azimuthal angle, so yeah, and it dependent on this your distance r. So I'm writing this in your like polar coordinates. So one thing to know, and this is your BL and this is DL. This DL would depend on, this would be the factor along the this row, and this would be the factor around your azimuthal angle. So this is how would you write this DL element in polar coordinates. Okay, let's first take a dot product, and then so you want to first take a dot product. Okay, now if you take a dot product, this with this will cancel out, with this will become 0. So the only thing that will remain is this d phi, and you will left with 2 pi rho d phi. This would go away because you're taking a dot product, so this become a scalar. So now you're left with this, and the only thing that is changing is this azimuthal angle. And what you're gonna do is you can so when you integrate over this b dl, what is changing is this this azimuthal angle, that this covering like this theta. So you can say this is the theta I need. Now basically what you can do, you can calculate this theta very easily. Yeah, so this is, so this so this is square root of 3a. This is square root of 3. This is a, you can calculate this side, and this is a, this is a, you can calculate this angle because this is 90. So we can do our arithmetic, and so I have tangent a divided by a, so this and this cancelled out, and inverse. Yeah, so this would be, so theta would be here, not theta like this, theta like theta 1, theta 2. Let's say this is theta 1, this is pi over 3. And the next thing is do the same. You have this angle AA, so tan of this would be tan 2, so this would be a over a, which is 1, so this would be pi over 4. Now you just add those. So theta would be theta 1 plus theta 2, which is 4, so this is 12 and 7 pi. So you plug in theta here and the answer becomes 7 pi over 12, so 7, this pi and pi cancel, mu I over 24. So answer is A. So this is a more mathematical way to do it, but you can also do it more physically, like kind of an approximate Ampere's law, and let's see how can we do that. Okay, now let's do the second way. So one thing you have learned about in um, Ampere's law is that this answer is when you go around the wire, when you enclose the wire inside the loop, this is equal to mu time I, right? Which mean if you enclose the wire, this is mu time I. So if you enclose the wire inside the loop, this is become an Ampere law, and this will be the answer, mu times A, and that is very easy. But if you have a loop where the wire is not enclosed, this thing is 0. That is clear. And then, but you have a case where it's an open path, not a closed one. So how do we apply Ampere's law? So one thing to notice is that, so in this area where you're looking at, where your path is located, right, it's not closing a loop, so you can't apply this Ampere law in that sense. But one thing to know, your magnetic field in this, so this is one of the equation of magnetic field. But when I'm looking at this area, uh, so when I'm looking at this area, this is 0, right? This is 0, so your magnetic field is acting like a conservative field if you just restrict yourself to this area, right? So your magnetic field is acting like a conservative field. So what is the thing in conservative field we can always use? It does not depend which path you take, right? Like if I go from here to here, or here to here, like here to here, like it doesn't matter as long as the paths are in um, if the it doesn't matter which path you take from point 1 to point 2, and that is what you can take advantage of, and this is what you can do, if you go so basically what you can do is you can consider a loop and see how much this area only, area how much this part of the loop contribute to this line integral, and you're gonna get your answer. So we know uh, 2 pi contribute mu um, I, and then 1 radian or whatever, 1 radian is gonna cost this much, and this theta is gonna um, contribute this much amount. So you have the same answer, and we have already calculated theta 1 and theta 2 previously, which came out to be 7 pi over 12, and you can plug that over here, and you get your answer, 2 pi 7 pi. There's nothing difference, pi cancels, 7 mu I over 24, right? So now you can calculate it like this if you're not comfortable if calculating a line integral, and if I don't think line integral is in the syllabus, but I could be wrong. The trick is like in this area you're calculating, this is the open loop, this is the open path, it's not closed, and magnetic field in this area is acting like a conservative field, which is not true for magnetic field in general, but if you restrict yourself from in this area, then it's kind of true. And what that give you is the advantage that it doesn't really matter which path you take, and this line integral, what line integral this contribute when you go 2 pi, and then you can just make this how much it will contribute if you just think about this part. So I hope you like this video, and I hope you understand something. So yeah, like, share and subscribe, and I will see you next time.